All right, so we're going to continue on Unit 4 today. So if you remember back to Monday, we calculated the wavelength and the frequency of waves. Today we're moving on and we're going to calculate the energy related to a wave. Okay, so that's what we're going to be building on today. All right, so think back now to Unit 3. Remember in Unit 3 we determined that Rutherford found the nucleus. So he found the nucleus, had protons and neutrons within the nucleus, and we have electrons around it. But once again, Rutherford didn't say where these electrons were located, how they were arranged outside of the nucleus, but they're there. So Rutherford's nuclear model was not complete. He didn't describe how the electrons were distributed. He didn't know what the attraction was between the nucleus and the electrons, right? He just said, we've got some negative particles outside of that nucleus. Okay, so that's what we're going to determine more about today. So in the early 1900s, scientists started studying experiments that they could not understand using that wave theory of light that we talked about on Monday. So remember we talked about waves. We said waves were continuous, right? Waves had a repetitive nature. Okay, but then they started seeing different experiments that couldn't really be explained by a wave. All right? So some scientists in the 1900s started looking into what they called the photoelectric effect. What this photoelectric effect showed was that there was an emission of electrons from a piece of metal when light shined on the metal. So what they saw here, we got a piece of metal, all right, we're shining a very bright light. Since this bright light was shining at the metal, it gave the metal enough energy to actually excite electrons and then have electrons bouncing off the surface of this piece of metal. What the scientists found out through this observation was that the light must have been at a minimum frequency in order to excite these electrons. There had to have been enough frequency in this light in order to give enough energy for those electrons to bounce off the surface. If light was only wave-like, any frequency would have caused this electron to bounce off. So then they started to determine that, well, light has other properties other than just being as a wave. Because when this light shone in a wave, the electrons bounced off, not in wave-like behavior. But when they bounced off, they also had a certain energy equal to the energy shown by the light. So this started to give them some ideas about electrons. Some ideas that, well, electrons don't necessarily behave like waves. They show single individual energies rather than bouncing off in a wave, even though the wave of the light came to the surface. They were ejected from the surface without wave-like properties. So at this point, the scientists were still just collecting little bits of data, all right, trying to piece together what are these electrons, where are they distributed, okay, what kind of properties do they exhibit. Any questions on the photoelectric effect? Okay, so Max Planck started studying these emissions, started studying these electrons that were being emitted by hot objects from the light shining on emitting the electrons. What he proposed was that hot objects do not emit electromagnetic energy continuously, because they didn't bounce back in the wave-like form as electromagnetic radiation has to be in wave form. They just bounce back as individual energy pockets. He called these small energy pockets quanta. Okay? What a quantum is a minimum quantity of energy that can be lost or gained by an atom. So that is the amount of energy as the electron was emitted from that surface, how much energy that object released. He did plenty of trials of this photoelectric effect, that he came up with an equation to determine what the energy is of that quantum, how much radiation was emitted in the form of energy. So here is the formula. Energy, that's how much energy is released, is equal to H times V. Max Planck was the one to determine this correlation here, this formula, so therefore he got to name his own constant. H is a constant, Planck's constant. And then V is what we calculated the other day, frequency. You need to know this formula. E is going to be an energy, or is the energy. It must be in joules. Abbreviation is J. Those are the units for energy. H here is Planck's constant. 6.626 times 10 to the negative 34 joule times second. Those are the units for Planck's constant. Joule times second. And then frequency, as we learned on Monday, same units. 1/2, hertz, s to the negative 1. Okay, any of those units, again, mean the same thing, so you can use them to plug them into this equation. So you will see what happens when I multiply H, Planck's constant, which is joule times second, times my frequency, which is 1/2. The seconds cancel, that's why we equal joules for our energy. Okay, so that's where the units come from. So H is always the same constant. Therefore, if I'm using this constant, my frequency must be in hertz. If it's not in hertz, megahertz, or something else, you convert it to hertz before you plug it in. If I give you energy, it must be in joules. If it's in kilojoules, you convert it first to joules, plug it in, then you'll solve for frequency. Okay? But Planck was able to make this determination that using his constant, using the amount of frequency shining into that metal plate, was therefore the amount of energy that was emitted from the surface. Okay, so that's what Planck did. Any questions so far? All right, so based on what Planck did, based on knowing wave-like behavior, it was determined that light can exhibit both wave-like and particle-like behavior. Meaning light can travel in waves continuously, but then light can also be emitted as an individual photon in a quantum amount of energy, not a wave-like behavior. So whenever that light is emitted, that was emitting a photon, and that can be shown using the exact same formula we just talked about. It's just stating here that that emission is called a photon, what is being emitted from the surface. And that photon exhibits particle-like behavior. That's why he was able to prove that light can exist as a photon, individual release of energy, and then light can also travel as it did into the metal plate in a wave-like behavior. Any questions? All right, so now we're just going to practice calculating that energy. All right, we're just going to practice the rest of the day using the two formulas that we've learned so far. So first we're just going to calculate energy. So it says, what is the energy of each of the following types of radiation? All right, so we have our formula. We're solving for energy. Energy is H, Planck's constant, times frequency. Here's my first value, 6.32 times 10 to the 20th, s to the negative 1. Since it says s to the negative 1, what is this value going to be then? Hertz. Okay, so what? Frequency, wavelength, energy, what is it? Frequency. Okay, so make sure you know your units. That way you know if I give you a value, you know what it is talking about. Okay, so this is frequency because we know s to the negative 1 are units for frequency. So now we just plug it in. We know Planck's constant is 6.626 times 10 to the negative 34 joule times second. We know our frequency here, 6.32 times 10 to the 20th s to the negative 1. So use your calculator here. Multiply those two numbers. And you should get an energy equal to, we have 3 sig figs here, so our answer should be in 3 sig figs. 4.19 times 10 to the negative 13th. Very good, joules. You should see that here. I have joule times second for Planck's constant. My units for frequency are 1/2. So what happens to my seconds? They cancel. That's how I know I'm left with a unit of joules. Any questions on that one? Okay, so now I have another frequency. It's given in hertz. That's how I know it is frequency. I'm calculating energy again, so I just plug it into my formula. Energy equals H times frequency. I know my H, Planck's constant. I know my frequency, 9.5 times 10 to the 13th hertz. Remember, hertz is the same as 1/seconds. So my seconds are canceling. I'm left with joules, which is what I'm trying to solve for. And I'm going to get I have 3 sig figs here, so 6.29 times 10 to the negative 20th joules. Any questions on calculating energy? These ones were pretty straightforward because I gave it to you directly in hertz. Remember, if I gave it to you in megahertz, or kilohertz, or anything other than hertz, convert it first to hertz, then plug it in. Any questions on those? Okay, let's look at these problems. All right, how many joules of energy are contained in a photon with a wavelength of 550 nanometers? Okay, here's my formula. I'm calculating energy, H times frequency. Right, this is what I'm trying to solve for, energy. So, I know Planck's constant, 6.626 times 10 to the negative 34 joule times second. E, or energy, is equal to H times, I would just plug it in my H here. Good question though? Now, do I know my frequency? No. I know wavelength though, right? Do I know a formula to relate wavelength and frequency? Yeah, we did that Monday, right? So, now I know my C, speed of light formula, is equal to wavelength times frequency. Y'all remember this from Monday? I know C. I know wavelength. So, do you think I could calculate my frequency and then plug it in? Yes. Okay, so now we're combining the two formulas together. If you know one, you can calculate any of the other two using these two formulas. So let's do that over the side, and then we'll plug in our frequency once we determine frequency, but we don't know it yet, okay? So know that our C, that was our constant speed of light, 2.998 times 10 to the 8 meters per second. Here's my wavelength. Can I plug this wavelength right into my formula? Why not? It's not in the correct units, right? So we got to do that first. So somewhere over this side, do that. Make sure I'm still on this computer screen. There we go. 550 nanometers. Nanometers is on the bottom so that it cancels. Meters is on the top. Which one's bigger, a meter or a nanometer? Meter. What's nano? 1 times 10 to the 9th, nano 9, very good. So now we're going to divide those two numbers. You should get 5.5 times 10 to the negative 7th meters. Now can I plug in my wavelength? Yes. So I'm going to plug in my wavelength here. 5.5 times 10 to the negative 7 meter. I do not know my frequency. That's what I'm solving for. So how do we solve for frequency? Divide my wavelength, right? So I get 2.998 e to the 8th divided by my wavelength. Gives me my frequency, 5.45 times 10 to the 14th. What are my units for frequency? Hertz, very good. Okay, so now I have frequency, which is what I needed to start with. Okay, so pay close attention to what's given to you in the problem. Don't just start plugging things in, okay, without making sure that you have the correct value, the correct unit to plug in, okay? We didn't have frequency, but we can find it, all right? So as long as you know what you're looking for, you know what you have, you can do it easily. All right, so now I'm going to plug in my frequency, which is 5.45 times 10 to the 14th hertz. Now I'm set up to finish. Now I can multiply those two to solve for my answer. How many sig figs should I have in my answer? Just 2, right? That 0 is a placeholder. So just 2. You get 3.6 times 10 to the negative 19th joules. Any questions on that? Y'all feel good about it? What I would encourage you, we're going to do another one together, so don't worry. But what I would encourage you, right when you see a problem like this, which you're going to be practicing a lot today, write down both of your formulas. Okay? Then start checking off what you know. I know C. Well, let's do it with this next problem. Let's see. The energy of a particular color of green light is 3.82 times 10 to the 22nd kilojoule. What is its wavelength in nanometers? Okay, so let's see what we've got here. We're trying to calculate wavelength. That's this. All right, I'm trying to calculate wavelength. So I encourage, write down both formulas. Figure out what I'm looking for. And then you have to ask yourself, okay, I know C, that's given. Do I know my frequency? No. So even though I want to calculate wavelength, I can't start here, right? Because I don't have the frequency I need to calculate it. So then I look over here. Do I know E? Yes, I do, kilojoules. I know joules are my unit for energy. So I know E. Do I know H? It's a constant. So I can calculate for frequency, plug it in, and then get my wavelength. Okay? It seems like a lot, but you can do it. Write down both your formulas. Figure out what you're trying to solve for, and then you'll know which direction to take. So let's do that. Okay, so here we have the energy. Okay, we already read it. We're given the energy So we need to start with this formula. We already determined that. So I'm going to write it up here. Energy equals H times frequency. Can I plug this energy in to the problem? No, why not? It's in kilojoules. Okay. But I know how to convert from kilojoules to joules, right? So let's do that. Over to the side, we have 3.82 times 10 to the negative 22nd kilojoules. If kilojoules is on top, I must put kilojoules on the bottom to cancel, and then joules on the top. What's bigger, a joule or a kilojoule? Kilojoule. So I put a 1 with my kilojoule, 1,000 with my joules. Multiply across the top, and I get 3.82 times 10 to the negative 19th joules. Now can I plug my energy in? Yes, you're right. Yes, you can. It's in joules. So I plug it in for my energy, 3.82 times 10 to the negative 19th joules. Do I know my H? Yes, it's a constant. We always know H. So plug it in, 6.626 times 10 to the negative 34 joule times second. I do not know frequency. That's what I'm solving for. So now I will divide 3.82 e to the negative 19th. Make sure you're using that E button so you don't have any calculator errors with the exponent. Divide by my H. Gives me my frequency. So, I hope you got 5.77 times 10 to the 14th. What are my units for frequency? Hertz, good. Well, can I stop there? No, the problem's asking for wavelength. Okay, wavelength. But I have another formula now here, right? That I know my frequency. I know my C, speed of light, so now I can calculate my wavelength. So we have, I'm going to use my frequency to plug it in and solve for my wavelength. Y'all ready to do that? All right, so we're going to plug in our C. We know C, 2.998 times 10 to the 8th meters per second. Thank you. I do not know wavelength. That's what I'm solving for, so I'll leave that as my variable. Thank you. I'll leave that as my variable, but I do know my frequency. So, let me plug that in. I can plug in my frequency that I solved for, 5.77 times 10 to the 14th hertz. Now can I solve for wavelength? Yes, so divide the speed of light divided by your frequency, and you should get the wavelength equal to, I got 3 sig figs, 5.20 times 10 to the negative 7th. What are my units for wavelength? Meters. Am I done? No. Why not? Man, Miss Nair asked me to go to nanometers. Okay, we can do it. Meters is on the top. Meters is on the bottom. Nanometers on the top. Meters will cancel. Meter is bigger. Nano 9. Multiply by 1 e to the 9th. And you get 5.20 times 10 to the second nanometers. Woo! That is as long of a problem as you can possibly get. Converting at the beginning, using both formulas to calculate, and converting at the end. That's as long of a problem as you can get, okay? Any questions on any of those steps? All right, so highly recommend, once again, writing your formulas, both formulas for every problem. See what you're solving for, see what's given, okay? Kind of map it out then. Well, what do I need to solve for in order to get my final answer? Would y'all like to do 2 more together? Yes? No? Yes? Let's do it. Okay. A laser emits light of frequency. What is the energy? Okay, so a laser emits light of frequency 4.74 times 10 to the 14th hertz. What is the energy of the light in kilojoules? So, let's write our formulas down. Sometimes you'll need both. Sometimes you'll only need one. Okay? So, what do we have here? What's our given? Our given is our frequency, V, right? What am I trying to solve for? My energy, my E. Oh, well, I just need my one formula, right? I don't even need to worry about this. Okay? Because my H is given. So as long as you're only solving for one unknown, you only need to use one formula. Okay? So that's what I'm saying. It's important. Write down both of your formulas. Look what you're trying to solve for, and then figure out where you need to go from there. So we don't know E. That's what we're trying to solve for. We know H, 6.626 times 10 to the negative 34. Frequency. I know my frequency. Can I plug this frequency directly into the problem?
Yes.
Yes. It's in the correct unit, so we can. It's just in normal hertz. 4.74 times 10 to the 14th hertz. My seconds, as you can see, will cancel, which is what I need in order to calculate for my joules. So here, I'll multiply across the top. Not across the top, there's no bottom in here. I'm too used to saying that. Multiply the numbers. You should get, we need 3 sig figs for our answer. So we should get energy is equal to 3.14 times 10 to the negative 19 joules. Can I stop there? It asks for kilojoules, all right? So now set up your conversion factor. Joule is on top, so I need to put joule on the bottom, kilojoule on the top. Kilojoule is larger, so that goes with my 1,000 joules. Joules will cancel, and then I'm set up. 3.14 times 10 to the negative 22nd kilojoules. Any questions on that one? So we only need one formula there. Okay, so write out the formulas, then you'll be able to see which steps you're going to take. Let's do one more together. A certain electromagnetic wave has a wavelength of 625 nanometers. What is the energy of the wave? All right, so let's write down our formulas. Okay. I'm trying to calculate for energy. Do I know H? Yes, it's a constant. Do I know my frequency? Nope. So can I start here? Nope. Let's do this formula. Okay, I know C. Do I know wavelength? Yes. So now I can calculate my frequency and plug it in order to solve for my energy. All right, so let's do that. We'll use our formula, speed of light, wavelength times frequency. We know C, it's a given, constant, 2.998 times 10 to the 8 meters per second. Okay, wavelength. Can I plug my wavelength directly in? It's in nanometers, so come over to the side. 625 nanometers. Nanometers on the bottom, meters on the top. Meters are bigger. 1 times 10 to the 9th nanometers. So when I divide, I should get 6.25 times 10 to the negative 7th meter. Now can I plug in my wavelength? Yes. 6.25 times 10 to the negative 7th meters. And I don't know my frequency. That's what I'm solving for. So in order to solve for frequency, I need to divide my wavelength over. You should get frequency is equal to 4.3 sig figs 80, the way it rounds, times 10 to the 14th hertz. Now I have my frequency. I know H. So can I calculate my energy? Yes. Okay, so now I'll use my energy formula. E equals H times frequency. I know my H, 6.626 times 10 to the negative 34. I know my frequency, I just solved for it, 4.80 times 10 to the 14th hertz. Bless you. So now I will multiply. And I will get my energy is equal to 3 sig figs, 3.18 times 10 to the negative 19th. What are my units going to be? Any questions on that? Okay, so this is it for the calculations in this chapter. We really have 2 more lectures to cover all the rest of the information, and we have to actually determine, this still doesn't tell us where the electrons are located. So we actually have to do that as well. The plan right now, unless anything changes, is that we'll do our 2 following lectures next week. And then your test will be on e-learning day, okay, the week of Thanksgiving. It's going to be open note. I will let you do open note. It will be on Schoology. If you can't access Schoology, that's no problem. I can get you a paper copy, and then you'll turn it either picture back to me through Schoology or turn it in after Thanksgiving break. Okay, so that's the plan right now. That way, traditional and virtual school can both do it on Schoology, and you can use open notes for this test only, and then we'll have time for 1 more unit before Christmas break. So, any questions?